For our team's foldable robotic project, we have decided to go with a Grasshopper bio-inspired foldable robot. Grasshoppers build up stored energy in their legs and can jump up to 40 times their body length. Using antagonistic muscle pairs, they charge up energy and release, springing them forward. We wish to replicate this ability in our foldable robot. Foldable robotics is a relatively new field of study in which laminate layers are pressed together to form cheap, fast, and easy to build robots. Foldable robots are made out of many different types of materials and pressed together in order to provide different properties at different locations, some for stiffness, some for flexibility. They're all connected using this pegboard, aligned and adhered in a heat press. Once all the layers are adhered together, it is then put into the laser for a final cut. Some parts, such as motor mounts, spring connections, and microcontroller mounts, have to be 3D printed. After the final cut, the robot is folded up and put together. Our jumping design goal required us to store energy that could be released instantaneously in order to jump. In the beginning, target weight and height were set in order to calculate the energy we'd need to store in order to reach that height. This allowed us to determine the number and stiffness of springs in order to reach that height. Shown here are the calculations for the final weight and height we anticipated. As you can see, the robot stores energy by moving the rack and pinion and stretching the springs using tendons in the legs. The gear teeth disengage and release, creating a jump.
The cantilever beam assignment helped us determine how the layer thickness affects our system. Here is a single layer, and next is a multi-layer laminate device. The multi-layer is consisted of 5 layers, 2 cardboard, 2 adhesive, and 1 film. Side-by-side comparisons show thicker laminates are more rigid under stress. Once the appropriate thickness was calculated, first pass and final pass cuts were created using pop-up CAD with appropriate hinge widths. A dynamic model was created using Unity. This dynamic model helped determine the number of springs we needed and the weight and mass that our robot would need to be for optimal performance. The optimal performance of our robot would be the highest jump possible with the least amount of stress on our robot itself.
The sensor our team is using is a BNO055 sensor. It comes with an accelerometer to measure our robot's jump acceleration. We connect to our sensor through a photon board. Our photon board allows us to send data both through a wire connected to our robot or over Wi-Fi. Wi-Fi communication removes any wires from interfering with our jump, but is slow compared to our other options. Both our photon board and accelerometer are mounted onto our robot. We then begin reading the accelerations and begin our robot's jump. The data is recorded on a computer for comparison. The maximum acceleration experienced by our robot was around 29 meters per second, smaller than what our simulation had predicted. We believe this difference to be due to the weight of our robot being smaller than what we had initially calculated, and our springs not stretching their full amount. If we were to go any further with this concept, we would reconsider the spring locations and the weight effectiveness of our design. Our jump wasn't as high as we would have liked either, and that would be the focus of any redesigns in the future.
Oh, here we go.
No!
Frick!